billion years later. This indicates kind of the expansion of the universe. Here there was a very fast expansion called inflation, and the conditions that we are looking at when we collide the protons together are as if we were looking at a very early part of the universe. You see over here, about a billionth of, I don't know if you can see the numbers, but about a millionth of a second after the Big Bang. So that's the kind of collisions that we create in a very small space, just where the particles are colliding. So where do we do that? That's the Large Hadron Collider, that accelerator. You see over, it's just outside of Geneva, Switzerland. So here you see Lake Geneva, and it's a ring that is about 17 miles in circumference, about 300 feet underground. Here is the CERN laboratory site. This is so big that it goes underneath just ordinary land around Geneva. And you see where the ATLAS experiment is located over here, and the CMS experiment over here. I like this picture because typically when a scientist of some kind shows you their experimental apparatus, you know, they put a quarter next to it or a ruler so that when you look at it, you have a sense of scale. When you do this one, here's our measuring. It's the airport. It's the Geneva airport that gives you the sense of scale. If you look inside the tunnel, what do you see? Well, what you will see is that it looks something like it. Well, it looks exactly like this, except it's connected. You see these very large magnets. There are about 1,200 of these magnets, superconducting magnets. They're there to bend the particles around in that circle, that 17-mile circumference circle. They were built a little bit like, you know, sort of a ship in a bottle. They came down through a shaft and then were moved into position. All 1,200 of these, and then this is an open end, and then you have to weld this to the next guy over here. So it was a big, big effort to try to do that. So what I want to do is give you a big sort of overview of our experiment and how it works. So I'll start with this place that you may recognize. This is us. And what I want to do is zoom in to where CERN is, so just outside Lake Geneva, and you start to see that over here. Here's Lake Geneva, here's Geneva itself. Around there then, here's Geneva. There you see the 17-mile circumference ring, which is underground. We're now zooming in over to the CERN site, and this is the ATLAS control room where a lot of the monitoring goes on, but the real action occurs 300 feet underground in this cavern that's attached to this ring of 17-mile circumference. So if you look inside, you see that the ATLAS detector, and we're going to pull apart the ATLAS detector over here, and what you see are specialized detectors for looking at particular kinds of elementary particles that will occur in the collisions. So this is our camera in that sense, and you'll see pieces fly off at us, and we don't have enough time to discuss it. It's called the tile calorimeter, optimized for a particular kind of particle. As we pull apart the onion over here and start to look inside, you'll see electromagnetic calorimeter. And you had, if you've been to previous talks, Nevis Labs has been involved with that, particularly for the electronics that you see around here. As you go in further, you come to what's called the inner tracker over here, and that's a device to measure very precisely where charged particles go. It's the same technology that's in your cell phone. And to give you a sense of scale, here's somebody walking on a detector. We don't like to walk on our detector like this. But it gives you a sense of scale. So as you pull back, that's a regular sized person. And you see that this thing is massive over here, right? It's almost 8 stories tall and about twice as wide. Now you see coming in on the sides, you'll see 2 red dots. They represent the bunches of protons. There's 100 billion protons in one, 100 billion protons in the other. They collide in the center of our detector. You use that equation, E equals mc squared, to produce new mass, new particles, and that's represented by all these lines that you see over here. Each one of those represents a particle that's coming out. And so we use this detector like a digital camera to take a snapshot, electronic snapshot of that collision, and try and measure all the particles that come out. So here's a view, just so that a sort of, again, artist rendition of this. Again, to remind you of the scale. I was trouble. here are regular sized people standing over here, right? Now, you don't need to know all these things, but here are the labels of the different kinds of detectors that we have that are specialized to look at the various elementary particles coming out. Again, as I say, if you press it, it's like, you know, it's 25 meters tall. It's about 7 or 8 story tall building, and it's about twice as long. It has about 100 million channels of electronics. Sometimes when I say that, people go, okay, round numbers, this thing costs $1 billion. So somebody says, okay, so this is a digital camera, 100 megapixel camera, $1 billion. I've got, I don't know, 20 megapixels in my pocket over here, and this only cost me $100. What's the big deal? How come? Well, one of the things is if I ask you your camera, how many pictures does it take per second? I don't know, 30, 60, something like that, call it 100. The thing for us is that we can take 40 million pictures per second. So that sets one of the reasons. And then, of course, it's this big because you have to see the particles over there, and you have to stop some of them, and you need a big detector in order to be able to do that. There's a picture of it here, and I sort of over there as well, which I show you. So this is actually the detector, and again, now you see a real person standing over here. Again, to set the scale, and this was in 2005 while it was being assembled.